Hey everybody, Corey and Victoria here. We are the Professors Du Bois, and welcome back to another lecture. Today we're going to be talking about bond properties as well as the calculating the enthalpy of reaction another way, and it is from using the bond energies.
All right, so let's start with bond properties, and we're going to talk about bond order, length, and strength. Now, we talked about bond order with our resonance structures, and the way we calculated bond order is we counted the number of bonds, and then we divided this by the number of sites to get a bond order. Now, if we apply this to a single bond, we have one bond bonded to one thing, so 1 divided by 1 is 1. A single bond has a bond order of 1. A double bond has a bond order of 2, and a triple bond has a bond order of 3.
If all of chemistry could be this easy.
I know. The single bond is the single bonds tend to have longer length than double bonds or triple bonds. So this is, if we're looking at a carbon-carbon single bond and comparing it to a carbon-carbon double bond compared to a carbon-carbon triple bond, we will see this trend in terms of length. And if we look at the strength, or the amount of energy it takes to break these bonds, or the amount of energy evolved when these bonds formed, we'll see that there's this similar trend that the single bonds have the lowest energy, longest length, lowest energy. Double bonds, they're in the middle, and the triple bonds have the highest energy, meaning it takes the most energy to break a triple bond. Also, the most energy is evolved when a triple bond is formed.
All right, there's another thing to consider with bond length other than the number of bonds between the atoms. And you can use your trends for atomic size to kind of be able to predict what a bond length might be. So here we have halogens bonded to a hydrogen atom. So we've kept the hydrogen consistent, so that atomic size is the same. But as the atomic radii increases as you go down the periodic table for the halogens, fluorine, chlorine, bromine, and iodine, they get bigger and bigger and bigger because they have more and more electron shells. Well, since they are bigger, their outermost electron is further away from their nucleus, and it's that outermost electron that's bonding with the hydrogen. So the nuclei between the length between the nuclei of the halogen and that hydrogen is going to increase as the atomic radii of the halogen increases. So you can predict the bond length from your trends of atomic radii.
So we've got a reaction here. We've got hydrogen, H2 gas, and chlorine, Cl2 gas, diatomic elements, forming 2 moles of HCl. We've got a balanced equation. These are all in the gas phase. And we're going to use bond energies to estimate the energy of the reaction, or the enthalpy, or delta H. And so we've kind of written this below, like, well, what is H2? If I draw a Lewis structure, that's a single bond, HH. Cl2 is also a single bond. And the HCl is a single bond. And we can estimate the delta H of this reaction by summing the bonds broken minus the sum of the bonds formed. So what's being broken? What's being formed? Well, the reactants, those bonds are breaking so that they can reform the hydrogen with the chlorine. So we've got one HH bond, single bond, broken, one chlorine to chlorine bond broken, and we're forming 2 hydrogen to chlorine.
Hold on
bonds.
1 moment, because this is energy in, right? So it takes energy to break the bonds. We're putting energy in, so we're tallying, or we're getting all of that energy. How much energy does it take to break everything?
Yep.
And then how much energy is released to put everything back together? And the difference between these two is whether it took extra energy to, was it an endothermic process or was it an exothermic process? And we'd be able to determine how much that is.
That's right. Going back to the enthalpies, a negative delta H would be an exothermic reaction. So
right. Okay, so here's an example, or this is the example worked out. The bond energies are usually provided. So this is usually either in a table or provided in the problem. Sometimes you can have the delta H of reaction. You might have to solve for one if one of them is missing. But it's simply tallying up all of the bonds broken minus all of the bonds formed. And we do this on a mole basis. So in your balanced equation, we have 1 mole of HH bonds right from up here. So we have one of these. we have 1 Cl minus, 1 mole of Cl minus, so we've got that here. And be careful, we have 2 moles produced, and we just have this one single bond here, so we have 2 moles of an HCl bond as well. So you just add them both together and subtract bonds broken minus bonds formed. And the interesting thing about this example that we gave you here is, okay, so this delta H of the reaction is negative 186 kilojoules. But if you notice that this is an actual formation reaction, so we went from our elements. So we have the hydrogen gas and the chlorine gas, and those are the elements, and it's making a compound. Now, the molar heat of formation is to make 1 mole.
Right.
So we can just divide this by 2, and now we've come up with the molar heat of formation of HCl.
Yeah, and it is correct. It is 1 mole of HH, but you can kind of simplify this a little bit when you look at the reaction and just say, I have 1 hydrogen to hydrogen bond here. And I mean, technically it is a mole, and you can see how moles cancel because the units are kilojoules per mole, but you can kind of take a step back and just say, okay, I've got 2 hydrogen to chlorine bonds, so I got to multiply that by 2. I don't know if that helps.
Right. So here's another example. So we're given these bond dissociation enthalpies. So this is how much energy it would take to break this bond. It's also the energy that it would take to form. Okay, it's just a different direction of the energy. So we have chlorine gas again, and this time we're reacting with fluorine gas and making ClF3. So what we want you to do when you have a problem like this is to write the Lewis structures. And the reason you want the Lewis structures is that's the only way you can see what bonds you have, that ones that need to be broken and ones that need to be formed. And the biggest difference between the last problem and this problem is that our product here is making, we have 3 Cl to F bonds for each of those molecules. So we made 1 molecule or 1 mole of molecule in the reaction, but it actually is 3 moles of those bonds.
Another reason to write that Lewis structure is sometimes you have a double bond, and you don't realize that until you write the Lewis structure. N2 is a triple bond.
Right.
So if you had a chart of values, an N single bond N would have a different value than an N triple bond N.
Very good point.
And with this is an enthalpy of formation, and that's why we have these fractions in here, but we don't want to be too afraid of those, even though they're a pain. So we've got the Cl-Cl bond here, and the energy is 243 kilojoules per mole, and I've got a 1/2 of the Cl2. So I'm just going to multiply that value by 1/2, or I could multiply by 0.5. The 3/2 for the F2 looks really intimidating. So I've got the F2 value at 159, and what I'm going to do is I'm going to multiply 159 times 3, and then I hit equals. I always do this in my calculator, and I have a very simple calculator. So I'm going to go 159 times 3 equals, divided by 2 equals to get my value. The again, looking at bonds, I can say, hey, I've got 3 chlorine to fluorine bonds in this, and then I can go to my chart. I got the 255. I multiply by 3. Bonds broken minus bonds formed. I get a negative delta H. This is an exothermic reaction.
All right, here's one for you to practice. Pause the video and give it a try. Make sure you draw your Lewis structures first.
Definitely draw your Lewis structures. And there is a little hint there with the nitrogen, and they gave the enthalpy for the triple bond.
We only gave you the triple bond, but oftentimes you have a whole table and you have to decide if it's a single bond or a double bond. And a very common mistake would be to assume that that nitrogen is a single bond, and it would be wrong.
So give this a try, and we'll show you the answers.
Here you go. And the difference, one of the big differences between this and the other problems that we gave you is that we have a coefficient for the NF3. So we have 2 moles formed, and each of those molecules has 3 NF bonds. So it's really 6 moles that you have to put in your problem.
That was a tricky one.
It was a tricky one. That's why we put it in there, to make sure that they wouldn't get caught when it's on an exam.
That's right. All right, that's it for today. We appreciate you guys watching, and stay tuned. We're going to do some more Lewis structures, I think.
Yeah, Just never ends. We're going to get into shapes next time.
All right.
Stay tuned for shapes. We've finally gotten to molecules, and we've finally gotten to how they're put together, and we're going to be able to assemble them and understand from these Lewis structures, what do they look like in 3 dimensions. So stay tuned for that. Bye-bye.